This problem deals with choosing the inductor value in a buck converter. The choice of the inductor is critical in determining the performance of the buck converter, whether it operates in CCM or DCM or a combination of both. This is the buck converter. In a buck converter, input voltage range is given 50 volts to 100 volts DC. Output voltage is 30 volts DC to be regulated. That means it has to be kept constant through feedback control. Power output range is 60 watts to 120 watts. That means when the voltage is changing from 50 to 100 volts, or when the power or the output current is changing, DC voltage output is being maintained at 30 volts in the converter through some control mechanism by changing the duty cycle. The switching frequency has already been chosen, 100 kHz. Treat the buck converter as ideal. The capacitor C is taken to be large so that the output voltage can be taken as near pure DC. Part A of the problem is calculate the minimum inductance L min such that the operation is in CCM under all operating conditions. A buck converter is most often designed to operate in CCM. Under CCM, the buck converter's efficiency will be very good. Currents will be lower than in a DCM design. So generally, CCM design is preferred. So here we are trying to choose an inductor in such a way that the operation is in continuous conduction mode under all conditions. There is a video in this series, PE2A3, which deals with the boundary operation between CCM and DCM, which essentially determines whether the operation is in CCM or in DCM. In case you have difficulty in following this problem, you may wish to go through that video. The switching period is 10 microseconds, 1 over 100 kilohertz. IOB is given by V0 Ts by 2L times 1 minus D. IOB is the boundary output current. The derivation of this equation is available in PE2A3 video. If the output current IO is more than IOB, the operation will be in CCM. If the output current is less than IOB, the operation will be in DCM. And this equation can also be written as V0 Ts by 2L times 1 minus V0 by Vin. D equals V0 by Vin is valid under the boundary condition also. So we would like to choose the L in such a way that under all conditions IO is greater than IOB. The input voltage range is given as 50 to 100 volts DC. So V0 by Vin maximum will be 30 volts divided by 100 volts, which is equal to 0.3, which is of course equal to D minimum. Likewise, V0 by Vin minimum will be 30 by 50 volts, which is equal to 0.6, which is of course equal to D maximum. So the V0 by Vin ratio range is between 0.3 and 0.6. The output current minimum will be minimum output power divided by 30 volts, that is 60 watts divided by 30 volts, that is 2 amperes. Likewise, I0 maximum will be 120 watts by 30 volts, which will be 4 amperes. So the V0 by Vin ratio varies between 0.3 to 0.6. I0 value goes from 2 to 4. This is the designed range of the converter. The converter has to work in CCM under this range of operation. So for operation to be always in CCM, the minimum of I0 should be more than the maximum of I0B. So I0 minimum should be more than or equal to I0B maximum, which is the maximum value of V0 Ts by 2L times 1 minus V0 by Vin. Here the same inequality is reproduced. So we have to consider the case when V0 Ts by 2L times 1 minus V0 by Vin is maximum. The only thing that is varying there is Vin. That means we have to consider the case when 1 minus V0 by Vin is maximum, or V0 by Vin is minimum, or V in is maximum. So we have to ensure that when V in equals V in maximum, the minimum output current is more than the boundary current. This is done by a proper choice of L. So the worst case you can see is I naught minimum and V in maximum. That means if you ensure that when V in is equal to V in maximum and I naught equal to I naught minimum, the operation is in CCM or at the boundary, the converter will always operate in CCM in all other cases. So the worst case operating point for ensuring operation in CCM always is at V in maximum and I naught minimum. So using this inequality, we can calculate the L value. I naught minimum is 2 amperes. V in maximum is 100 volts. So 2 amperes must be greater than V naught Ts by 2L times 1 minus V naught by V in max. We can substitute all the values except L. From this inequality, we can calculate the minimum L. So the minimum L will be 30 times 10 power minus 6 divided by 2 times 2 times 1 minus 0.3. So we can calculate the minimum inductance as 52.5 microhenry. So if you select this inductance value, then at the worst case, when input voltage is maximum and the output current is minimum, the operation will be on the CCM-DCM boundary. At all other cases, it will be in CCM. In order to be on the safe side, generally it is a practice to take a slightly higher value. You may take 5% more, 10% more, or even 20% more. Next, we will do the corresponding problem with DCM as our desired operation. As I mentioned earlier, generally, we would not like to design a buck converter or its derivatives to operate normally in DCM under full load conditions. This is because of efficiency considerations. Here we will do it as a practice problem. Calculate maximum L, L is equal to L max, such that the operation is in DCM under all operating conditions. Here, I naught has to be less than I naught B under all conditions. So what that implies is the maximum I naught should be less than the minimum I naught B. I naught maximum should be less than or equal to I naught B minimum. When it is equal, we will be operating on the boundary. I naught B minimum means the minimum of V naught Ts by 2L times 1 minus V naught by V in. That means minimum of 1 minus V naught by V in. That means maximum of V naught by V in. That means minimum of V in. So the worst case condition here occurs at V in minimum and I naught maximum. Our choice of inductance must be such that we ensure operation in DCM or on the boundary when V in equals V in minimum and IO equals IO maximum. So the worst case operating point for ensuring operation in DCM always is at V in equals V in minimum and I naught equals I naught maximum. And we have put V in equal to V in minimum equal to 50 volts and IO equal to IO maximum equal to 4 amperes. We can bring the L to the left hand side and then L will be less than L max. L max will be 30 times 10 times 10 power minus 6 divided by 2 times 4 times 1 minus 30 by 50, that is 0.6. If you calculate this, it is 15 microhenry. So the maximum inductance is 15 microhenry. If you choose 15 microhenry, under the worst case, the operation will be at the boundary. On all other cases, it will be in DCM. Usually again, we will give a safety margin. This time we will give it the other way so that the inductance is not 15 microhenry, maybe 14, maybe 13, so that the operation is always in DCM for the range of operating conditions given. Next, we will do part C. Determine the values of the normalized input voltage range and normalized output current range. Use base V0 normalization. In previous videos, we developed two types of normalization. One to use the input voltage Vin as the voltage normalization factor, and the other to use the output voltage V0 as the voltage normalization factor. Both of these normalization methods are covered in the video PE2A6. Since we are regulating the output voltage to be constant, it is convenient to use base V0 normalization here. That's what we will do. And here we are trying to find the normalized values of the input voltage range and the output current range. The voltage normalization factor Vn is the output voltage V0, 30 volts. So what we will be normalizing is the input voltage Vin. Vin n max, the subscript n refers to the normalized value. So Vin n max is Vin max by V0, and Vin max is of course 100 volts. So that is 100 by 30, that is 1 by 0.3 or 3.333. This is the normalized maximum input voltage. V in N minimum is the normalized minimum input voltage is V in minimum divided by the normalization factor V0. That will be 50 by 30 or 1 by 0.6 or 1.667. So the normalized input voltage range will be between 1.667 and 3.333. When we are plotting the normalized characteristics, we would like to plot 1 over V in N versus ION. This is because 1 over V in N is VO by V in, the gain of the converter. So it is convenient to plot the gain of the converter versus ION, the normalized current. So we will introduce a variable y equal to 1 over V in N, and we will plot y versus ION. So we can calculate what is the y max value and the y minimum value. Y max value will be 1 over V in N minimum, that will be equal to V0 by V in minimum, that will be equal to 0.6. Y minimum equals 1 over V in N maximum, that is equal to V0 by V in maximum, that is equal to 0.3. Next we will do the current normalization. The current normalization factor in base V0 normalization is given by Ts V0 by 2L. Ts is 10 microsecond, V0 is 30 volts, L is something that we need to determine, so we do not know it yet. So this IN value will depend on the L value. So ION max will be 4 amperes divided by the current normalization factor IN. ION minimum will be 2 amperes divided by the same current normalization factor IN. So the ratio between ION max and ION minimum will be 4 by 2, which will be 2. The actual normalized current values will depend on the L value chosen. That is the goal of this problem. We will use these normalized voltages and currents to redo parts A and B on the characteristic curves. So next we will do part D. Determine the worst case operating points in A and B once again using base V0 normalized characteristic curves this time. So Y max we just now found that equals 1 over V in N minimum, that is equal to V0 by V in minimum, that is equal to 0.6. We also found Y min that equals 1 over V in N maximum, that equals V0 by V in maximum, that equals 0.3. We also found the ratio between the normalized currents ION max by ION min equal to 2. This is the normalized characteristic curves of the buck converter based on base V0 normalization. The x-axis is the normalized current ION, that is the output current IO divided by the normalization factor V0TS by 2L. The y-axis is y equals 1 over V in N, where V in N is the normalized input voltage. Y also equals V0 by V in the voltage ratio of the converter. This shows the complete characteristics. The CCM region on the right hand side, the DCM region on the left hand side, and the straight line is the boundary between CCM and DCM. Each of the curve is for one duty cycle, 0.1 to 0.9. We can mark the Y range and the ION range on these curves. Let's do that. And this is Y minimum 0.3, this is Y maximum 0.6. As the voltage is varied from maximum to minimum, along the y-axis, Y will vary from Y minimum to Y maximum. Likewise, along the x-axis, it shows ION minimum and ION maximum. As the current varies, the operating point will move from ION minimum to ION maximum. This rectangle represents all the operating points of this converter. ABCD is the rectangle. So the complete characteristics that are plotted shows all the possibilities with a buck converter. Whereas in this design, we are only using this particular range within this rectangle. Notice that we do not actually know the value of ION minimum and ION maximum. So we have arbitrarily chosen the ION minimum, and ION maximum is double that. This corresponds to one particular design of the converter, one particular choice of L. Here the operation is completely in CCM. All the operating points of the converter fall within the rectangle ABCD. We can notice that point A, that corresponds to ION minimum and Y minimum, that is the closest to the CCM-DCM boundary. Now we will use this idea in determining the L minimum value. Again, on top, Y max is 0.6, Y minimum is 0.3, and ION max by ION minimum ratio is 2. We will now place the rectangle such that at the worst case, it is on the boundary. So the rectangle that we saw earlier has to be pushed a bit to the left-hand side like this. Again, the rectangle is ABCD. This is Y minimum corresponding to maximum input voltage, and this is Y maximum corresponding to minimum input voltage. So again, this is ION minimum and ION maximum corresponding to minimum output current and maximum output current. You can notice that Y minimum is 0.3, Y maximum is 0.6. That is what we want in our design. ION minimum in this case is 0.7 and ION maximum is 1.4, so that the ratio is 2. We have placed the rectangle in such a way that point A just touches the boundary. That is the worst case operating point. If point A is in CCM or on the boundary, all other operating points are automatically in CCM. The graph makes it visually very clear. So the worst case operating point is ION minimum and Y minimum. Worst case operating point is indicated by the red dot. So point A corresponds to Y equal to Y minimum, which is the same as V0 by V in maximum, and ION minimum corresponds to IO minimum by TS V0 by 2L. So the worst case operating point for CCM operation always is at V in equal to V in max equal to 100 volts, IO equal to IO minimum equal to 2 ampere. This is the same worst case operating condition that we got earlier. If you choose the inductor in such a way that the operation is on the boundary under this condition, the operation will always be in CCM. The ION minimum value is 0.7. You can read it from the graph or you can use the equations to get it. Y minimum is 0.3. ION minimum is 0.7. IO minimum is 2 amperes. We know that they correspond to each other. So using these two, you can calculate and show that L minimum equal to 52.5 microhenry, the value that we got earlier. Next, we'll repeat part B, this time using these base V0 normalized characteristic curves. Again, Y max is 0.6, Y minimum is 0.3, ION max by ION minimum equal to 2. The rectangle ABCD shows the operating region for our CCM design. We are now going to find the worst case operating point for operation in DCM always. So we are going to draw another rectangle, small a, small b, small c, small d. This time all within the DCM region. And the worst case now is point C, the lowercase c. And that is placed in such a way that it just touches the boundary. And that is indicated by this red dot. Notice again, Y minimum is 0.3, Y maximum is 0.6, and ION maximum to ION minimum ratio is again maintained at 2 because that's what we want in our design. So the worst case operating point occurs at ION maximum and Y maximum. ION maximum means the output current maximum. Y maximum means V in minimum. So the worst case operating point occurs at V in minimum and IO maximum. V in minimum is 50 volts, IO maximum is 4 amperes. So in this problem, the worst case operating point for choosing an inductor such that the operation is always in DCM is V in equals V in minimum equals 50 volts and IO equals IO maximum equals 4 amperes. This is the same result as we got earlier. So ION max is 0.4 and the corresponding IO max is 4 amperes. So using these two, we can show that L max is 15 microhenry. Again, as I said, we will give a slight safety margin. Instead of using 15 microhenry, we will use a slightly smaller inductance. Again, it's not often that you see buck converter designs completely in the DCM region. If you know of any applications where the buck converter is designed to operate in DCM, even under full load conditions, please post it in the comment section. One can also choose L such that the operation covers both CCM and DCM. That means under full load condition, it will be in CCM. As you go towards lighter loads, it will shift to DCM. One such example is shown here. We can mark A, B, C, D here as shown. As you can see that the operating region straddles the boundary line. So in this region, it is CCM. In this region, it is DCM. So at higher currents, as you increase the load current, the operation shifts to CCM. As you decrease the load current, the operation can go into DCM. Such a design approach is quite common. This ensures that under full load condition, the efficiency is high. We also ensure that the inductor is not chosen to be too large. So here's a problem. Please try this problem out for yourself. Determine L minimum such that the operation is always in CCM for load currents greater than 70% of full load current. Full load current is 4 amperes, so 2.8 amperes and above, the operation is always in CCM, irrespective of the input voltage. So the question is, what is the minimum inductance that will satisfy that requirement? That's the end of this problem video. If you like this video and this series of videos, please subscribe to this channel and click the like button. Thank you.